Okay, everybody seems like they're here now. How's everybody doing? Six 6.1, 6.2. Six point four, 6.5. 6, 7. 11.1 and 11.13. Okay, that's all we're aspiring to get to for the next exam, your fourth exam and your last exam. So let's go over here to modules. Go here to 6.1. Okay, so now we're going to be talking about exponential functions. Okay, an exponential function is a function of the form f of x. Some a times some b raised to the x power. Okay. So there's some conditions where a can't equal 0. Or else you wouldn't have a function at all. You just have it equaling 0. And also b can't equal 1. Okay. So let's talk about some exponential function examples. Okay. How about f of x is equal to 2 times 3 raised to the x power? That's an example. How about f of x is equal to negative 5, 2 raised to the x power? How about f of x is equal to 13 times 17 raised to the x power? All these are examples of exponential functions. I can't see over where you're writing. Oh yeah, here we go. Thanks for letting me know. So let's talk about evaluating exponential functions. So how about I evaluate this function right here? Let's say, what is f of 0? Well, f of 0 is just 2 times 3 raised to the 0 power. Oh, but that's just 2 times 1, which is 2. Let's evaluate it at f of 2. F of 2 is just the same thing as 2 times 3 raised to the 2nd power. Oh, but that's just 2 times 3 squared, which is 9. And then you multiply them and you get that equals 18. What's f of -3? Okay, so that's just 2 times 3 raised to the -3 power. Notice that's the same thing as 2 times 1 over 3 raised to the +3 power. Notice that this is the same thing as 2 divided by 27. So that's how we evaluate exponentials. Okay. So let's talk about exponential growth. Functions that model exponential growth. Talk about exponential growth. Here's an example. The population of India in 2013 was 1.25 billion. So at 2013, population of India was 1.25 billion. With an annual growth rate of about 1.2%. So I'll write annual growth rate as AGR, annual growth rate 1.2%. So that's the population growth rate. So now it says that the situation is represented by a population function with respect to time, sub p of t. And that's equal to our initial value, 1.25 billion, times this 1.012 raised to the t power. There you go. Where t is the number of years after 2013. So, what will the population of India be in 2031? So the way we do that is we evaluate this function at some years after 2013. In 2031, how many years have passed by? Well, we just got to subtract them. So what's 13 minus 31, or what I mean is 31 minus 13. Let's make sure that is 18 years. Okay. So 18 years go by from 2031 from 2013. So we put 18 and evaluate it for our t, because the function represents the population t years after 2013. So notice that this is just going to equal 1.25 times 1.012 raised to the 18th power. And that's going to be a lot of people. Let's see how much that is. It's approximately 1.55 billion. That's a lot of people. 1.25 billion was already huge. 1.55 billion is even more. Okay. So how did we set up this situation? Well, notice that the function assumes an initial condition value. That's what comes over here. Then this is actually related to the annual growth rate. How is it related to 1.2%? Well, 1.2% is the same thing as 0.012. And what you do is you add 0.012 to the value of 1. And so that's when you get 1.012. And that's why that's 1.012. Because if it was just at the value 1, first of all, it wouldn't be exponential growth. Second of all, there would be no growth. Because you could raise 1 to any power, it would remain 1. So notice that when it's growth, we're going to add whatever percentage it is in a decimal notation to the value 1. And furthermore, if there's exponential decline or exponential decay, what you would do is you will subtract the percentage from this value 1. So let's create an exponential model when we don't know an initial value. Recall the exponential function is of the form a b raised to the x. Okay. So let's say we have some type of exponential function and it passes through 2 pairs of points. Let's say it goes through -2, 6. And let's say it passes through 2, 1. What does this mean? Well, both of them mean when we evaluate the function at the x component, it outputs the y component. So f of -2 should equal 6. But again, that we know that that's a times b raised to the x, but x is replaced with a -2. So we know this equation holds. 6 is equal to a times b to the -2nd power. And that's just the same thing as a divided by b squared. But what does this other piece of information reveal? Well, it says that f of 2 is equal to 1, which is equal to a times b raised to the 2nd power. Because that 2 replaces the x. Okay, so now we have 2 equations. What we can do is we can solve for a in both of them. Here, a over b squared is equal to 6. So that implies that a over here is equal to 6b squared. Furthermore, over here, this implies that A is equal to 1 over B squared. So A is equal to A. We can set these equations equal to each other and eliminate a variable. And this is what we get. And then I can multiply both sides by B squared, revealing that I get 1 is equal to 6 times B to the 4th. Now I can solve for B. I divide both sides by 6. So I get 1/6 is equal to B to the 4th. And that implies that I know what B is. B is equal to the 4th root of 1 over 6. And that means B is, well, plus or minus, that is. And that means it's going to be equal to 1 over the 4th root, because the 4th root of 1 is 1 of 6. So this is what B is equal to. And we can plug that into a calculator and approximate it. That's approximately 0.63. So that's what our B is. So we know B. Now we should be able to find A, because A over here is equal to 1 over B squared. So I can find our A that's equal to 1 over B squared, but that's 0.63 squared. So that's equal to what we get when we plug that into our calculator. That's approximately 2.24. Or I mean 2.44. That's what I mean. That's our A. And that's our B. So our exponential function model over here can be rewritten based off of this information. We can now plug in what is A and what is B to get the complete model. So then our model f of x will equal our A, which is 0.63, times our B, which is 2.44, raised to the x power. Now let's talk about compound interest. The amount with respect to time is equal to the principal amount invested times 1 plus the percentage, the interest rate, divided by the amount of times compounded per year, times RT. Not times, but raised to the NT. This is NT. So there's multiple ways that interest is compounded. Sometimes it's compounded annually, like once a year. Other times it's compounded quarterly, 4 times a year. Other times it's compounded monthly, so 12 times per year. So it all depends on the way it's compounded. So let's assume that you have $1,000. And let's say you want to leave that in the bank, and you want to know how much you'll have in your bank if you leave $1,000 in there for 20 years if it's compounded monthly. So if n equals 12, and let's say the interest rate is at 2%, your R is equal to 2%. Okay? And your T, the amount of years you want to put it in there, is you want to leave it in there for 20 years. Let's figure out what your new account balance will be in 20 years. That implies we're getting A of 20. So that equals the $1,000 you had plus 1 plus your rate, which needs to be divided by 100 because it's a percent. So we put 0.021 because we moved the decimal places over twice. Oh, not 2.1, but just 2%. So we move this over 1, 2. So it's 0.02. We divide this by the number of times it's compounded per year. And if it's compounded monthly, it's 12 times per year. And so this is going to be 12 times 20. Let's see what this gives us when we compute this. 1,000 times 1 plus 0.02 divided by 12. Everything raised to the power of 20 times 12. $1,491. So that implies after 20 years, your $1,000 would become $1,491. So you made nearly $500 by leaving that $1,000 in your bank. That's not very smart because if you use that $1,000, you can invest it in some other idea. Maybe you can generate more money, but some people don't want that. They just want to leave it and let it rack up the interest, and that's fine. To each their own. Okay, now let's talk about continuous growth and decay. Continuous growth and decay is modeled by the function a of t is equal to a e to the rt. Where e is that special number in your calculator. Okay. It's the number e. Actually, what e is, it is the limit as n approaches infinity of 1 plus 1 over n raised to the n. This is what equals e. Very strange. But anyways, Let's do the same situation as before. Before you had $1,000 and you wanted to leave it in the bank for 20 years, and the rate was 2%. Now, how much money will you have in 20 years if it's compounded continuously? Well, let's calculate it. A of 20 will equal the principal amount invested times E raised to some rate 0.02, your interest rate, times the amount of years, 20. So let's see what we get here when we do this calculation. $1,491.82. $1,491 and 82 cents. Whereas when you did it compounded monthly, you got $1,491 and 32 cents. Waiting 20 years and having a few cents different, that seems pretty ridiculous. Okay. Let's do something more interesting. Let's talk about radioactive decay. Okay, so we have a radon 222. It's a type of element, a type of radioactive element. It decays continuously at a rate of 17.3% per day. So its decay rate is equal to 17.33%. We'll just drop one of these threes here. How much will 100 milligrams of radon 222 decay in 3 days? So here's our question. How much of 100 milligrams of this radon 222 will decay in 3 days? Again, the decay rate is modeled by a continuous exponential function. Okay. But we notice that since it's decaying, that there needs to be a negative on this rate. Okay. So let's talk about the amount that we have, and this needs to be a function of t. Let's talk about the amount that we'll have after 3 days, okay? So F of 3 is going to equal to the initial amount that we had, 100 milligrams, times e raised to the negative 0.173, because you move the decimal place over twice, times the amount of days, 3. Okay, so when you do the calculation, what we end up getting is that's approximately 59.5. It's approximately 59.5 milligrams. So the question was, how much of it will decay in 3 days? This is telling you how much of it is left after 3 days. The amount that decayed is not 59.5 milligrams. That's the amount that's left. The amount that decayed after 3 days is 100 milligrams minus this much, 59.5 milligrams. Okay, so this is almost 60. So it's going to be around 59.5 milligrams. No, 49.9, 49.5. Because, yeah, no, I think I did that wrong again. Let me do this here. It's 100 minus 59.5. Now it's 40.5. 40.5 milligrams. So this is how much decayed in 3 days. The question asks, how much of the 100 milligrams will decay in 30 days? So 40.5 milligrams of it decayed. That means 59.5 milligrams of it remains after 3 days. Okay, that's section 6.1. Time to move on to 6.2. Graphs of the exponential functions, okay? Very easy. They're asking us to graph stuff. We know how to graph stuff, okay? An exponential function of the form f of x is equal to b to the x. Let's graph. For instance, find what the graph of f of x is equal to 2 to the x looks like. Create an f of x table as usual. Let's pick some numbers, symmetrical numbers about the origin, -1, 1, 2. And let's evaluate the function at these various values. F of -2 is the same thing as 2 raised to the -2 power, but that's 1 over 2 to the second power. So that's 1 over 4. F of -1 is the same thing as 2 raised to the -1 power, but that's the same thing as 1 over 2 raised to the positive 1 power, which is the same thing as 1 over 2, which is 1/2. F of 0 is the same thing as 2 raised to the 0 power, but that's just 1. F of 1 is the same thing as 2 raised to the 1 power, but that's just 2. And F of 2 is the same thing as 2 squared, which is 4. So then we We tabulated our results. Now it's time to graph. Okay, go to -2, -1, 1, 2, and let's see where these values range. You go 1, 2, 3, 4 at the highest. Okay, so at -2, we find 1/4. -2, we find a fourth, we put a dot. -1, we find a half, we put a dot. 0, we find 1, we put a dot. 1, we find 2, we put a dot. 2, we find 4, we put a dot. So once we're done with doing that, like always, we just connect the dots. That's your function in yellow. Easy as that. Okay, and just like last time, we can have vertical shifts, horizontal shifts. So let's erase this. All right, now let's consider the function f of x is equal to 2 to the x plus 2. All right. What is f of -2? That's just 2 to the -2 plus 2. But that's just like last time, 1/4 plus 2. What's f of -1? That's like 2 to the -1 plus 2. That's like 1/2 plus 2. What's f of 0? That's just 2 to the 0 plus 2. And that's just 3. What's f of 1? Oh, that's just 2 to the 1 plus 2. And that's just 4. What is f of 2? Oh, but that's just 2 squared plus 2. That's 4 plus 2, which is 6. So then, come over here at -1. We find -1. We go here at -2. We find this -2 is a fourth plus 2. So we go to 2 and we move up a fourth and we put a dot. We go to -1. We find 1/2 plus 2. So we go to 2 and then we move up a half and then we put a dot. Then we go to 0, we find a 3. We find 3, we put a dot. Then we go to 1, we find a 4, we put a dot. Then we go to 2, we find a 6, and we put a dot. Once we're done doing this, what do? We just connect the dots. And this is our function f of x is equal to 2 to the x plus the 2. Notice that adding a 2 just caused a vertical shift. If we subtracted a 2, it would cause a vertical shift down. Adding values causes a vertical shift up. Subtracting values causes a vertical shift down. So how do we do a horizontal shift? How about a function f of x equal to 2 raised to the quantity x minus 1 power? Okay. Well, then f of negative 1, or I mean f of negative 2, is the same thing as 2 raised to the negative 2 minus 1 power. That's 2 to the negative 3. That's the same thing as 1 over 2 to the third power, so that becomes 1/8. 1 over 8. F of negative 1 is the same thing as 2 to the negative 1 minus 1. That's the same thing as 2 to the negative 2. That's the same thing as 1 over 2 squared. And that's the same thing as 1 over 4. What is f of 0? That's the same thing as 2 to the 0 minus 1. That's the same thing as 2 to the minus 1. That's the same thing as 1/2. What's f of 1? That's the same thing as 2 to the 1 minus 1. And that's the same thing as 2 to the 0, which is just 1. What's f of 2? That's just 2 to the 2 minus 1. That equals 2 to the 1, which is just the 2. So what do we get here? At negative 2, we find a 1/8. We put a dot. At negative 1, we find a 1/4. So we put a dot. At 0, we find a 1/2. So we put a dot. At 1, we find a 1. And we put a dot. At 2, we find a 2. We put a dot. And what you'll notice here is when you connect the dots, what's in red has been horizontally shifted to the right version of what's in the yellow. So subtracting values inside the exponent like that will cause it to shift to the right. Adding values inside the exponent will cause it to shift to the left. It's counterintuitive, but it's true. You saw how it happened when we tabulated it numerically here. Okay. So in general, our exponential functions are of the form f of x is equal to ab raised to the x minus or plus c plus or minus d. Okay. The d causes vertical shifts. Plus d is a vertical shift up. Minus d is a vertical shift down. Is plus or minus c. Minus c is a horizontal shift to the right. And plus c is a horizontal shift to the left. So what you guys are going to have to do is go practice this on your own. You'll get plenty of practice from the homework. So that's 6.2. Practice plotting functions the way we are here. Create an f of x table, tabulate the results, create dots, connect the dots, and recoup your thoughts. Logarithmic functions. Let's talk about logarithmic functions. Okay. Let's talk about how it relates to exponential functions. Let's say some y is equal to some b raised to the what I mean is b raised to the y is equal to some x. Let's say b raised to some y is equal to some x. Okay. We all know what undoes addition. The reverse of addition is subtraction. We all know what undoes division because the reverse of division is multiplication. But what undoes exponentiation? What is the inverse operation of exponentiation? Meaning raising things to the power. So exponentiation, let's say I have x is equal to y. The operation of exponentiation here, raising both sides to the second power, does this. Y squared is equal to x squared. So what undoes exponentiation? Well, some people say, well, just take the square root of both sides. And you'd be right, that undoes the exponentiation. But there is something that is more generalizable than just taking the square root. Okay? And that is the logarithm. So when I take the log of both sides, the log base b of both sides, the logarithm needs a base as well. What we get is this becomes the log b of b raised to the y is equal to the log base b of x. But there's something known as the power rule of logarithms. Let's talk about the power rule of logarithms. For a log base b of some x raised to some power p, the power rule, which I'll call PR, the power rule states that that exponent inside the parentheses on top of the x can come out in front of the expression. This is the power rule. Okay? Next, we must create an intuition for what logs are asking. So what if I say log base 2 of 8? What does this equal? So when I ask log base 2 of 8, what does that equal? It's asking you a question. It's saying 2 raised to what power is equal to 8? That is what it's asking you. It is saying 2 raised to what power, and I can put that question mark right here, because that's the same question mark that's going to go over there. 2 raised to what power is equal to 8? Who could tell me what that is? That's right. 2 raised to the 3rd power is equal to 8. So that implies that this expression is equal to 3. So log base 2 of 8 is equal to 3. What is log base 2 of 4 equal to? That is a question. It's saying 2 raised to what power will equal 4? Anyone can give me an answer to that? That's right. 2 raised to the 2nd power is equal to 4. Okay? So that's kind of the intuition we have for logs. All right? So now, that means what is the log base 2 of 2? That's the question, that 2 raised to what power is going to be equaling to 2. And clearly, that implies that log base 2 of 2 is 1. So that allows us to segue to this argument here. Log base b of b to the y should equal log base b of x. And I claim that now when we use the power rule, we bring this y over here, so this becomes log base b of b, right? And then, like over here, log base 2 of 2 is 1. Log base b of b is 1 as well, because b raised to the 1st power is equal to b. So this whole thing is 1. So 1 times y is just y. So we get y is equal to log base b of x. Now, the logarithm allows us to define a new function, log of x, log base b of x. Let's find what the domain and the range for this function is. Log base b of x is equal to y. This is some function of x, some f of x. So we can plot it, can't we? Okay. Let me ask you this question. What is log base b of 0 equal to? Notice that this implies, this is the question, b raised to what power is equal to 0? What power can I raise b for it to equal 0? This is a tricky one, because usually when you raise things to powers, they grow. They get bigger and bigger and bigger. So how is it that we're raising this thing to some power and it's getting so small it's going to 0? Because the question mark is equivalent to negative infinity. What do you mean by that, Professor Niazi? Well, notice that b to the negative infinity is the same thing as 1 over b raised to the positive infinity. And anything raised to the positive infinity is an infinity. And so it's 1 over infinity. And that equals 0 because an infinitely large number stuffed into a small number like 1 results in the overall ratio of that approaching 0. So that's why log base b of 0 is undefined, because it equals negative infinity. And that means it's equal to undefined. Okay, so that's why the log function actually ends up looking like this. And you know what? Although that was beautifully drawn, I'll do it in yellow to make it distinct. Here's x, here's y. I'm about to draw log base b of x. This is f of x is equal to log base b of x, where there's a vertical asymptote right where the y-axis is. Why is that? Well, the function can never be evaluated at 0, because at 0, it's outputting a negative infinity. And that's why as you approach 0 from the right, the function is dipping towards arbitrarily low values, all the way down towards negative infinity. Furthermore, as you increase in value, the function is actually going towards positive infinity. So the domain of this function is going to be equal to, we can't include 0. So 0 to infinity is the domain. And what is its range? The range is all reals, because it goes all the way down to negative infinity and all the way up to positive infinity on the y. So here's a question. We've already discussed what the domain is, but you could ask, why can't we take the log base b of a negative number, like let's say negative x? Well, that's asking you a question. B raised to what power is equal to some negative number? If b is a positive number, there is no power you can raise that b for it to equal a negative number. There is no power. If you have a positive b, if b is assumed to be greater than 0, then there is no power you can raise b for it to become miraculously some negative number. That's why, another reason why the domain is defined the way it is. Not only can you see that by understanding it as this limiting case, but also you can see that it would lead to a contradiction, because a positive number raised to any kind of power does not equal a negative number. even if you raise it to a negative power, that negative power doesn't turn it negative, it just causes reciprocals. So like 3 raised to the negative 2, that's just 1 over 3 squared, but that's just 1 over 9, but 1 over 9 is still a positive number. Okay, so this b raised to the y is equal to x. This is called the exponential form of a logarithm. And this log base b of x is equal to y. This is called the logarithmic version. These two are equivalent. They're just two different faces of the same coin. I showed that to you, haven't I? Need I show it to you again? All you need to know is the power rule. If you start off with the exponential, b raised to the y is equal to x. Take the log base b of both sides. Then you get log base b of b to the y is equal to log base b of x. But notice with the power rule that y comes down out in front, so we get log base b of b. But log base b of b means to what power must I raise b for it to equal b? And that means the power is equal to 1. So this whole thing is equivalent to 1. So y times 1 is just y. And that always equaled this right-hand side, log base b of x. So we have traveled from the exponential version all the way to the logarithmic version. Now let's do this via some concrete examples. What about log base 6 of the square root of 6 is equal to 1/2? Let's convert this logarithmic expression to an exponential expression. I've not told you how to undo a log. And this is how you undo a log. I showed you how to go from exponential to logarithmic. How do we go from logarithmic to exponential? Before we can even do this problem, let me erase it. I haven't showed you how to travel back. I showed you how to get there, but I didn't show you how to go back home. So let's start off with the logarithmic now. Log base b of x is equal to y. Now, the way you get rid of a log is you raise both sides. You exponentiate. You say b raised to the power of log base b of x is equal to b raised to the power of y. Every time you raise a number to the power of something that involves the log base b, and these are the same base b, the log base b, everything disintegrates, and all you get is what was inside the parentheses, x. So for example, if I had log base 3 of x is equal to y, then over here I would say 3 raised to this side, 3 raised to this side, and then I would get x is equal to 3 to the y. So b is just a placeholder for any kind of number we could want. So now that I've given you that, what is log base 6 of square root of 6 is equal to 1/2? Well, we want to get rid of this log. It's base 6, so we use the number 6. This, because they have like bases, causes everything to disintegrate except what's inside the parentheses. So then you get 6 raised to the 1/2 power is equal to the square root of 6. Aha, I mean, that's true. 6 raised to the 1/2 power is equal to the square root of 6. That's how you can show that that's true. Let's do more practice with logarithms. Find y if it's equal to the log base of 4 of 64. What is y? Well, y is asking you a question. Well, y is a question. It's saying 4 raised to the y power is equal to 64. So how do we determine what that is? Is when you go from here, you just put a 4 here, you get 4 raised to the y power is equal to 64. That's how you get from here to here. But how do you know what y is? Okay. Well, y is the power that makes 4 raised to that power equal to 64. Notice 4 squared is 16. What is 4 cubed? Well, that's 4 times 16. Well, that's 40 plus 24. That's 64. So that implies y is equal to 3. So let's talk about the common logarithm. The common logarithm is log base 10. If we just write log without specifying a base, that implies it's log base 10. Always. It's secretly implying that this is log base 10. Okay, so here's a question for you. What is log of 100 equal to? Well, since there's a secret 10 over here, it's asking you the question, 10 raised to what power is equal to 100? And we all know that when you square 10, it equals 100. So that's what you get is 2. So what is the log of 1,000,000? What is the log of 1,000,000? It's really not that hard because you know it's log base 10. the power at which we raise 10, it adds a 0. So 10 squared, we get 100. That 2 added, you get 2 zeros to that. So notice that we got 1, 2, 3, 4, 5, 6 zeros. So it's 10 to the 6. That implies log base 10 of a million is equal to 6. Okay. Now let's talk about the natural logarithm. This was the common logarithm. Now we're going to talk about the natural logarithm. Typically denoted as ln. Every time you see a ln, that's really the log base e. Okay. So, what is the ln of e? So that's the same thing as the log base e of e. But this is a question. It's asking you a question. E raised to what power is e? Clearly, the only power we can raise e for it to restore itself is the power 1. So that means that the natural log of e, ln of e, is equal to 1. What is the ln of e to the 14th power? Oh, well, that's just the same thing as this question. That is equivalent to saying, what is the log base e of e to the 14th power? Oh, but that's a question. It's saying e raised to what power is equal to e to the 14th? Clearly, that implies that our question mark is equal to 14. So that implies that the natural log of e to the 14 is equal to 14. And that is everything for 6.3. By the way, guys, if you guys are having, if you guys want more resources on this stuff, feel free to check out my YouTube channel. I have YouTube videos on logarithms, more practice problems. I have YouTube videos on how to graph exponential functions and functions in general. So I provide you with as much resources as I can. The ball is in your court, and it's going to require practice. So moving on to 6.4. I will also note that we will definitely cover the material prior to our last few days of class. And I will be out of town during the last 2 weeks of your class periods. So we will have to have reviewed everything by then before you can take your final. And there are resources available to you both for this course and on my YouTube channel that you can reference so that it can help you with that last test. Okay, so moving on to 6.4. Graphs of logarithmic functions. We've already graphed logarithmic functions. Okay. But what we can do is actually put some more of a spin to it. Okay. We just did some arbitrary logarithmic function, log base b of x is equal to our f of x. Let's find the graphs of some different examples. Let's do f of x is equal to log base 2. Of x plus 2. Or let's say 3. Okay. Graph this. Find this domain. Do everything. Find its range. So the way we do that is we always create our f of x table. All right. And we know that we can't have what's inside here being equal to 0 as before. So we have to say we want this x plus 3 to be strictly greater than 0. It can never equal 0, right? So we want what's inside there to be greater than equal to 0, meaning we want x to be greater than -3. So we already discovered the domain. It's all the values greater than -3. So for all values greater than -3, let's try -4, or greater than -3. -2, -1, 0, 1, and 2. So then we have to talk about what is f of -1. I mean f of -2. That's the same thing as log base 2 of -2 plus 3. This is the same thing as log base 2 of 1. So what is log base 2 of 1? That is a question. It asks us the question, 2 raised to what mysterious power will cause it to become 1? That mysterious power is 0. Because when you raise any number to the 0th power, it becomes 1. Remember, we proved that together. We proved that because in general, any value x to the 0th power is the same thing as x to the power p minus p. And notice that that's the same thing as x to the p times x to the -p. Notice that's the same thing as x to the p divided by x to the p. And that's just 1. So x raised to the 0th power, anything, any x, anything raised to the 0th power is equal to 1. And that's why. So that's why we get a 1 here. What is f of -1? F of -1 is log base 2 of -1 plus 3. So then we get log base 2 of 2. That is a question. It says 2 raised to what power is equal to 2. Clearly, that is 1. Oh, over here, that last value that I put in should equal 0. The question mark was 0 for last time because 2 raised to the 0th power equals 1. So I had to just put a 0 there. And over here, 2 raised to the 1st power should equal 2. So that's why I put in 1 here. Okay. I tabulated the wrong result. Happens to everybody sometimes. What is f of 0? That's log base 2 of 0 plus 3. That's just log base 2 of 3. That's our question. This is 2 raised to what power is equal to 3? Well, that answer is not straightforward. It must be some type of fraction, fractional power. So I'm just guessing right now. How about 2 to the 4/3? Because this would then equal the cube root of 2 to the 4th, right? 2 to the 4th, 2 squared times 2 squared. Actually, 2 to the 4th is 2 cubed times 2. So this is 2 times cube root of 2. So this doesn't work. That doesn't work. So we want it to equal 3. As you can see, there will quickly be results where it is non-obvious as to what that power is. What power can I raise to for it equal 3? How about I do, instead of 4/3, how about I do 3/4? 2 raised to the 3/4 power. No. How about I do 2 raised to the 5/2? So this means we're taking the square root of 2 to the 5th. But that doesn't work either. Okay. So you won't be expected to find logarithms of values that aren't integer values, so whole number values. You will have to actually ask the calculator what log base 2 of 3 is. There are ways to do it by hand, but there is no exact value for it. So log base 2 of 3, we plug this into our calculator. Why doesn't it like this? Okay, let's try. Log calculator. Log base 2 of 3. So that's approximately the decimal 1.58. So that implies that the question mark is approximately 1.58. But you guys get the picture. You'd be able to graph this thing, but you won't be given something like what we have here. You will only be given something where you can evaluate it for specific values. But what you'll notice is that causes a horizontal shift. And when you add, it shifts to the left. So normal log base 2 would look like this. This other guy would be shifted to the right by 3 units. 1, 2, so 1, 2, 3, it would look like this. And let's have that guy in yellow. So what's the domain of this logarithmic function? Let's say log base 5 of x minus 2 plus 1. Well, the domain is only affected by what's inside this log, right here. We must ensure that this is greater than 0. It cannot equal 0, or the logarithm becomes undefined. So we add a 2 to both sides. That determines the domain. Put this on the real line. Here's 0. Here's 2. It says for values of x greater than 2. So we put parentheses and we put squigglies here, so the domain should equal 2 all the way to infinity. See here. Okay. I will note that in general, for f of x is equal to log base b of x, you can cause a stretching of the function or a compression by multiplying this by some constant. So a log base b of x, if this is your g of x, compared to f of x, if a is a number that is greater than 0 but less than 1, like a fraction, this will lead to a stretch. But if a is a number that's strictly greater than 1, this will lead to a compression. But you know, this stuff is good for asking visual intuition questions. But at the end of the day, you could create an f of x table, and it would reveal to you that this is the truth. Okay. So let's say we're given a graph. How do we find the equation? So given a logarithmic graph, how do we find the equation? So we have something like this. What's the equation for it? Well, we know in general, a logarithmic equation has the form negative or positive. We'll put it negative here. A log, we got an x plus 2 because it's clearly been shifted to the left by 2 units horizontally. We also notice that at x equals -1, -2, at x equals -2, the function exhibits a vertical asymptote. It doesn't look so clear for what I've drawn, but from what you will be provided, you'll see that, oh, here at x equals 2, there's a vertical asymptote. So that's why that there's this x plus 2 business here, because for x equals -2, that is, we'd said that the domain has to be, this inside the log has to be greater than 0, x plus 2. So this implies that the domain is all the x that is greater than -2. So at -2 is when you find your vertical asymptote of it being undefined. So that's why we get this plus 2 here. All right, but we don't know the stretch or the compression, and we don't know the vertical shift. So we'll put that plus k. What we do know is that f of 0 is equal to 0 visually. Do we not? Yes, we do, because f of 0 goes through the origin. So then this becomes -a log of 2 plus k is equal to 0. All right. We also can see that at -1, it's at +1. That f -1 is equal to +1. So another piece of information we have is f of -1 is equal to +1. That's equal to -a log of 1 plus 2 plus k. So that means 1 is equal to -a log of 3 plus k. All right. So in either one of these equations here, we can solve for one variable and then plug it in and find the other. Or a function in orange is -a log base 10, so the common log of x plus 2 plus k. All right. So let's take this right here. We get k is equal to a log of 2. Over here, we get k is equal to 1 plus a log of 3. But k is equal to k, so that means a log of 2 is equal to 1 plus log of 3. Oh, and it's got an a here. All right. So then we can combine the terms that have the a together and let them hang out on one side of the equation so we can factor out the a. So then I get a log of 3 minus a log, this should say 2. A log of 2 minus a log of 3 is equal to 1. Then we can factor out an a. So I get log of 2, a number that we can evaluate, minus log of 3, a number we can evaluate once we plug it into the calculator, both of them, is equal to 1. So now I can solve for a. A is equal to 1 divided by log of 2 minus log of 3. So we can solve for a that way. Once we know a, once we compute what this value is, let's see here. 1 divided by log of 2 minus log of 3. That's negative 5.67. That's our a. Then once we know a, we can solve for k. Let's say we can use this equation right here. If k is equal to a log of 2, that means k is equal to negative 5.67 log of 2. Log of 2 is just a number in the calculator if we plug it in. So that means k is equal to negative 1.71. So we've been able to determine what this function is. This function in the orange, we were just seeing its graph visually, and through this step-by-step process, we were able to extract what the unknown a and the unknown k were. And so we get our orange graph as f of x is equal to negative 5.67 log of x plus 2 plus, which is now plus this negative value, minus 1.71. This is our function. And that is 6.4. On to 6.5. talk about logarithmic properties. What is the log base b of 1? Well, that's a question. Again, it says b raised to what power will make it 1 always? The power that will cause any number to equal 1 always is 0. So we have this property, that the log base b of 1 is equal to 0. What is the log base b of 0? Well, that's a question. It's saying b raised to what power will cause it to equal 0? But we discussed that that's part of defining the domain. The question mark is really negative infinity. And so that's why the domain of the function is 0 to positive infinity. Because when this is negative infinity, we have b to the negative infinity is equal to 1 over b to the infinity, which is equal to 1 over infinity, which is equal to 0. So actually, that's part of why the domain is the case. The other one what we want to talk about is log base b of b. That's equal to 1 because b raised to the first power is equal to b. So those are some logarithmic properties. Let's talk about some other logarithmic properties. Let's talk about the product rule. This says that the log base b of some m times n is equal to log base b of m plus log base b of n. This is a very important rule. It's called the product rule. Furthermore, we have something else called the quotient rule. It says that the log base b of m divided by n, such that n does not equal 0, clearly, because we can't divide by 0, at least not in this mathematical context, without it being defined properly. That's equal to log base b of m subtracted by log base b of n. So, what? Like, how can we use this? So, what about I take the ln, the natural log of x, y? What does that equal? Well, by the product rule, the natural log of x, y is the same thing as the natural log of x plus the natural log of y. Also, what about the natural log of x divided by y? Oh, well, the quotient rule says that this is equal to the natural log of x minus the natural log of y. Okay? So, that is too easy. Let's do something more complicated. And the product rule, the quotient rule, is now inside your brain, so I can erase this. So how about we say expand the expression? How about we say, what is the ln of x squared y cubed divided by z to the fourth power? How can we expand this? Meaning, write it out as a series of ln's. So first we use the product rule. By the product rule, becomes the ln of the numerator. Oh, actually, what I mean is the quotient rule. So, quotient rule. Utilizing the quotient rule, the numerator, ln of the numerator, minus ln of the denominator. Okay, that's what we get there. Then, now, we're going to use the product rule here. So then we get ln of this x squared plus this ln of this y cubed minus this ln of z to the fourth. All right. Now, what we can do is the power rule. Saying that the powers can come out in the front. So we've expanded the expression. Okay. Let's do another example of expanding the expression. How about we have the log of x, y, z divided by 3. First, we'll use the quotient rule. So we get the log of the numerator minus the log of the denominator. Then there's no power rule to do over here. We're basically done, but there's about 2 product rules, one for this product and one for that product that we could pull off. So let's just group this as a product with this x. So using the product rule here, we get that this is the log of x plus the log of yz minus log of 3. Then using the product rule here, we get this is fully expanded to be the log of x plus the log of y plus the log of z minus the log of 3. But it's not just expansion that we can do. We can also do contraction. Or condensation, so condense So let's condense an expression. How about 3 log of x plus 14 log of y minus 13 log of z plus 4 log of pi. Let's condense it to just 1 log. So over here, we can use the power rule first. Power rule to bring these powers inside. So then we get log of x cubed plus log of y to the 14 minus log of z to the 13th plus log of pi to the 4th power. Once we've done that, once there's no coefficients out in front of the log, now we can use the product rule here. Okay. So then doing the product rule here, we get that this is just the log of x cubed times y to the 14th. And rearranging these guys, we get this is plus the log of pi to the 4th minus the log of z to the 13th. I rearrange them so that it forms a suggestive sequence of terms, because here we can use the quotient rule. So reproducing that, log of x cubed y to the 14th, I mean. Now doing the quotient rule here, we get this is plus the log of what's here is pi to the 4th. And what's with the minus, this term z to the 13th. Then moving the calculation up here, we can use the product rule right here to express this as 1 log. So it's going to be x cubed, y to the 14th, pi to the 4th. Multiplied, or I mean divided by that z to the 13th. So notice we got this thing, this huge expression here, and we condensed it to this expression. Let's do another example. What about the ln of z minus 12 ln of pi plus 13 ln of x cubed? Condense this expression. We can use the quotient rule here to rewrite this as ln of z, which goes into the numerator. Well, actually, let me not jump the gun yet. We can't do quotient rule yet. We have to use the power rule here. So let's use the power rule to bring this up here, and the power rule to bring that up there. So this becomes ln of z minus ln of pi to the 12 plus ln of x to the 39. Why is that? Well, it's because if we restore this as a power here, this becomes x cubed raised to that new power 13. But that's the same thing as x to the 3 times 13. And thus it becomes x to the 39. Now we can use the quotient rule. So this becomes ln of z divided by that pi to the 12 plus this ln of x to the 39. Then we can use the product rule between these guys and bring the calculation over here. So this becomes the ln of z x to the 39 divided by pi 12th power. All right. If this stuff is confusing you, you guys need to go back to the definition of product rule and the quotient rule and practice. You got to look at the practice problems, and you also have to go find YouTube videos like mine or other references on the internet that give you some examples. I try to explain it as clearly and thoroughly as possible, but I know I am surely I am speeding pretty fast here because we talked about the product rule, we talked about the quotient rule, we talked about the power rule, we talked about expanding, and we talked about contracting. And so we've gone through quite a bit. The only thing we haven't gone through in this section is the change of base formula. And what I'll do is we'll cover the change of base formula. And actually after that, this section will be over. And I will let you guys go after that because I've been going very rapidly. And it is like drinking from a fire hydrant probably for you guys right now. I recognize that and I know that, but at the same time, I have to do this because I won't be here for those 2 weeks for the end of the semester to be able to lecture over these things. So I have to do it in advance. Change of base formula. The log base b of m becomes the log base. So you change your base to log base n. Okay, and so what goes up here is your m, and what goes down here is your b. Okay, so this is just a formula. This is the change of base formula. It went from base b to base n. So what does that mean? Well, it means, let's say I have log base 2 of 3, like we did before, and that was really hard to evaluate. We didn't know how to evaluate it. Well, I could change it to log base 3. Right? Where up here, we get the 3, and down here, we get the 2. But, you know, in terms of actually computing what that value is, this doesn't help a whole lot, because this ends up becoming 1 over log base 3 of 2. And the log base 3 of 2 is just as hard as figuring out as the log base 2 of 3 analytically. But it does demonstrate the change of base formula. Over here, 2 is playing the role of B, 3 is playing the role of M. And N, apparently. I should have picked a different number. Let's do a different change of base. How about log base 4 of 17? Let's say I want to convert that to log base 5. Applying the change of base formula, the 17 goes here, 4 goes over here. So log base 4 of 17 is the same thing as log base 5 of 17 divided by log base 5 of 4. Okay, so that's it. That is it for section 6.5. So we have 1, 2, 3, 4 sections remaining. Next class period, we will easily be able to get through those and start doing an overall review for your final test. Let's see here. Today is November 11th. Right. So, yeah. So it's 1 week. Okay, so we got one, after this week is over, we got 1, 2, 3 weeks, and then you take your final the week after that. So your final will be due, let's check your calendar. Your final exam will be where's the calendar here? New calendar. Oh, it's in December here. Yeah, your fourth exam will be December 10th. A Thursday, December 10th. And what I'll do, I'll move all your assignments to be due the day before that, on the 9th. Let me just do that. Let me move all your homework to be due at that point. To give you more time, and so no one is like, hey, can you move the due dates? Because now I've already moved them to the farthest time that I can do for you. Give you the maximum amount of time possible. Well, I could give you one more day, but you'll be busy taking the exam. So don't push it. That one more day is not, I don't want to put it on that day because that's too many assignments. If you procrastinate, then that's that. Okay. So can you repeat that? My connection is not stable. All I heard was December 6th. Okay. I did not mention December 6th. I mentioned December the 10th. That is when your last exam in here will be. Your exam number 4 is December the 10th. I have pushed all of the homework assignments to December the 9th, the day before your test is due. Also, we have how many weeks? After this week, 1, 2, 3 weeks. And then after that, the 4th week is the test week. So I will be here for another 2 weeks. But after that, the last 2 weeks I will not be here. So next class period, we'll go over the rest of these right here. 6.6, 6.7, 11.1, and 11.3. And then we'll do review. Then the class period after that, we'll just do all review. And then after that, there will be no more class because I will be out of town. And I won't be able to run class. So we got this class is over with. So then after that, we got one more class and then another one with me. And then it's done. I won't be here anymore. But you guys will still be in school. You guys will still have to, you don't have to show up to Zoom conference or anything like that though. But you're still having to work your homework out and take your exam. I'll just be out of town and I can't lecture. So that's why I've been going so fast. I kind of went fast here. It'd be nice to go through 3 sections per class period. And so it's not fully rushed, but it's been a little rushed. It's kind of like you guys are drinking from a fire hydrant, but that's okay. I know you can handle it. And sometimes that's just how life is. I don't feel as bad as I would if I hadn't created a huge YouTube channel filled with a bunch of video tutorials on how to do problems just like this on all these sections. So you guys are well taken care of in that sense. You're not neglected, not that neglected. How does that sound? Okay. Because I've been making you drink from a fire hydrant, I'm gonna end class 15 minutes early. So unless anybody has any other questions, I'll see you guys next week. No questions? All right. See you guys next week.